Okay, so we're going to continue our Chapter 5 discussion here. We're looking at satellites. So this involves circular rotation and gravitation. So in the problem statement here, we want to determine how high above the Earth's surface a geosynchronous orbit satellite must orbit, and then determine satellite speed. So before I had said that keeping a satellite orbiting the Earth is all dependent on its velocity. So why now all of a sudden is this one asking about height? Well, it all has to do with the definition of geosynchronous. A geosynchronous satellite is a specific kind of satellite that orbits the Earth in such a way that the satellite is always directly above the same point on the Earth. So in order for that to occur, it has to be on the equator, because the equator is the only point on the Earth where you can stay above that one point and rotate about the center of the Earth, and since that's the direction that the Earth spins, that's where the satellite has to be, right on top of the equator, and that point will just go round and round and round, and the satellite will stay right above it. So the velocity is predetermined for a geosynchronous satellite. The velocity is that it has to revolve around the Earth once per day. So the period is 1 day. So the frequency is is 1 revolution per day. So we want to know how high above the Earth it needs to be. The height is going to determine the r in the equation. Let's get into it here, and perhaps you'll see what I'm talking about. So we want to start by applying Newton's second law of motion. The sum of forces is equal to mass times acceleration, which is going to equal mass times velocity squared over r, because that's what centripetal acceleration is. So the satellite is going to, it's geosynchronous, it's going to rotate at the same rate of speed as the Earth. So what is its velocity going to be? It's going to be 2 pi r divided by t. So it's going to be 2 pi. And what is the radius? Well, that's what we want to determine. It should be a pi. R is what we're going to solve for. And t. What is t? Well, it's 24 hours in a day multiplied by 3,600 seconds per day. Okay, so that's going to be 2 pi r over 86,400 is 24 times 3,600. So that's how many seconds it is. So 2 pi r over 86,400 is going to be the velocity of this satellite. Now, if we set the centripetal force to be equal to the gravitational force to keep our satellite in orbit, then we're looking at g, the gravitational constant, times m times the mass of the Earth, the mass of the satellite times the mass of the Earth, over r squared. That's the gravitational force. That's going to have to equal the mv squared over r centripetal force. And our velocity, we said, was 2 pi r over 86,400. And we have to square that and divide it by r, the radius. Okay, and so we can simplify that a little bit. So when we square something inside the parentheses, we're going to end up squaring both the top and the bottom. So this is like squaring the numerator, squaring the denominator. And let's just, since this is in the denominator, let's move it down here. So in other words, this is equal to m times 2 pi r squared divided by r times 86,400 squared. And okay, and so the reason I'm doing this is so I can kind of simplify my two r terms here. I can pull out the r squared times m times 2 pi squared over r times 86,400. That will cancel out this r, and I'll be left with just an r rather than an r squared. So let's see here. Now I've got g m m e over r squared is equal to r m times 2 pi squared over 86,400. Oh, and I just realized I made a slight mistake here. I forgot to continue to carry this squared. So that's something to watch out for. I've seen students do this as well, accidentally dropping an exponent throughout the solution of a problem. So it's 86,400 squared. So don't forget to keep carrying those exponents throughout the problem. Okay, so let's try to get this r over to this side of the formula now by multiplying both sides by r squared. So that'll leave me with g times m times the mass of the Earth equals r squared times r is r to the third times m times 2 pi squared over 86,400 squared. And now I can get rid of the m, that divide by that m, the same m over here, the mass of the satellite. So that'll cancel out and that'll cancel out. So I'm just kind of working my way step by step, simplifying this formula. Now I've got GME equals r cubed times 2 pi squared over 86,400 squared. Okay, so now that we've got all of the r's here on the same side of the equation, kind of isolated, this in the r cubed, we can move everything else over to the other side, because r is ultimately what we're trying to solve for, the height above the Earth. So r cubed is going to be equal to g me times 86,400 squared divided by 2 pi squared. Okay, so let's move this on to the next slide now. Okay, so we left off with r cubed being equal to GME times 86,400 squared divided by 2 pi squared. And so final step would be r equals the cube root of GME times 86,400 squared divided by 2 pi squared. Now, g is a constant and the mass of the Earth is a constant, so we just need to plug into those last couple variables, and we've got our answer. The radius is going to be the cube root of so G is 6.67 times 10 to the negative 11th. The mass of the Earth is 5.98 times 10 to the 24th times 86,400 squared. And then let's divide all of that by 2 pi squared. And crank that all into your calculator. If you do it correctly, you should find that the radius is 4.22 times 10 to the 7th meters. So that's how far above the center of the Earth our satellite needs to be. So if we want to know how far above the surface of the Earth that needs to be, we would need to subtract the radius of the Earth from our answer. So the radius of the Earth, if you remember, we wrote this down earlier, is 6.38 million, so that's times 10 to the 6th, meters. So if we wanted to know the height above the Earth that our satellite needs to be, the height would be 4.22 times 10 to the 7th minus 6.38 times 10 to the 6th, and that is going to equal so that should equal, let's see here, 3.58 times 10 to the 7th, and that is the height above the Earth's surface that our satellite needs to be, and that's in meters. So if we wanted to convert that to kilometers, move the decimal point 3 places to the left, it would be 3.58 times 10 to the 4th kilometers is the height above the Earth that our geosynchronous satellite needs to be. Now, part B of the question asked, okay, so what is the velocity of the satellite? To calculate the velocity of the satellite, if we just look back to right here, earlier in our solution, we had already found that the formula for velocity, that's one of the very first things we did, is equal to 2 pi r over 86,400. So to find the satellite speed, the velocity is equal to 2 pi r over 86,400. And that's going to be 2 pi times the radius we found was 4.22 times 10 to the 7th meters divided by 86,400. And that should equal approximately 3,070 meters per second. So that would be the velocity of our geosynchronous satellite at a height of 4.22 times 10 to the 7th meters above the center of the Earth.